the the number of X-rays passing through a particular area. Is that okay? That is what is going on. But if we are talking about the hardness of X-rays, we define it in terms of energy, wavelength, or what? Or frequency. Please, is it a little bit clear? So because of that, anytime we are defining X-ray, most of the times we express it in what? In kilovolts, which I'll explain it to you later. Now, if a material has more penetrating power, we call it a hard X-ray. And if it has less penetrating power, we call it soft X-ray. So when we take within the same X-ray, X-ray 1 and X-ray 2, the illustration at the top here, let's look at this. Which one will be a hard X-ray? Which one will be soft X-ray?
The hard will be 2 and then the soft is 1.
And the soft is 1. That is all. Is that okay? So hard X-ray and soft X-ray. And because in hospitals, the soft X-rays is used directly on our skin and other things. X-rays is mostly used on our skin and other things. We mostly use at the hospital part is the soft X-rays. Is that okay? And when you go to the airport and other security checks, they mostly use the hard X-rays because that one they are not using directly on your skin. It is passing through your material to check what is inside. Is that okay? So they mostly use the hard X-ray. But in terms of medical purpose, they mostly use the soft X-ray. So let me ask this the class a question. If we are talking about both the intensity and the hardness of the X-rays, which one kills more? Which one is very powerful? If we are very good, the hardness of the X-ray, because that is where the energy lies. Is that okay? It could be that the sun is very, very scorching. But even when you stay in the sun, it may not kill you. You have a lot of photons on your skin. But let's say it's just UV radiation, and you have a small portion that you has been exposed to. It may harm you. Is that okay? So the energy, the wavelength, and the frequency is very, very important. Now, I've mentioned a lot about the application. Is that okay? And maybe we will not go through it again. But has anyone done a CT scan before? Do you know a CT scan?
I don't know this, sir.
Okay, but anyone, do you know a CT scan?
No, okay. Sir.
No, that is fine. So let me go and show it to you right now. So I'll stop this slide. Then I'll share screen. Then maybe I'll share this.
Is it the one that they call the MRI?
Okay, MRI is a little different from CT, depending on their mechanism. Okay. So I'm showing something on the screen. Are we seeing it?
Yes.
Yes, sir.
Have we seen something like this before?
Yeah.
So Madam was asking about MRI. So this is MRI. This is CT. They have a little difference, which I'll talk to you about it later. So let's keep this machine in mind. Now, I have also done a CT scan before. I have done a lot of things before. So, and I went for one workshop too it was a radiation workshop. I think Ghana Radiation Society or something. They did one workshop in Cape Coast and I attended too. So this is how it works. You know, as we take X-rays, let me show you X-ray. Okay, so a very typical example of X-ray, maybe this one. Okay. Can we see this one?
Yes.
Yes, sir.
Very good. So you can see the fact that we can position the X-ray, then look at only one part. But the question is, with X-rays, you don't have the flexibility to look at a 3D. When I say 3D, when you go to the hospital, it's only this kind of picture they can give it to you. If your bone at the front part, that is all. We don't know what is at the side. We don't know what is beneath. That is all. If there's something behind this bone, this bone may hinder it from us seeing it. Is that okay? And that is why the CT scan is very important. So when you stay in a CT scan, and let's say it's something that you want to take in your head, I was having some abnormal pulses around my ears. So they made me check a CT to check if my veins and arteries there are okay. So when you go, you just lie down like this. Of course, you move all your watches and everything. Then you wear an overall. You sleep on this bench, and the machine takes you inside. But the radiographer doesn't stay with you. They have a chamber that they stay in, and you'll be left in that room alone. And their chamber is having a glass that is separating you and them. Is that okay? Because of the radiation exposure. So they will just be controlled with machines. And at the end of the day, this has a chamber inside that rotates like this. Is that okay? It rotates around, and it's able to give us a 3D pictorial of what we want to look at in your head. Is that okay? So X-ray can give us only one form of this image, but the CT can give us a different side and angle of your what? Of your head or the body we want to pick. Are we seeing the difference?
Yes, sir.
Yes, sir.
So I'm moving out. So any question to this so far? So that is just brief description of X-ray and X-ray application, and in terms of the normal X-ray machines that we use, and the CT that we use. Is that okay? Okay. Yes, Sir Lucky.
Yeah, yes, sir. Sir, I came across a question. They said, briefly explain why the target, which is the hot metal, sorry, the metal, I mean, the target is always hot during a X-ray operation.
Come again.
I said, I came across a question. They said that explain why the target of an X-ray is always hot.
The target of an X-ray is always hot.
Yes, sir.
Okay, so you can explain this in terms of the energy that we are bombarding it with. Is that okay? And I told you that we are talking about a very high energy. So you can explain that one pertaining to that. And I think another question that may be even at that angle is why the metal that we are bombarding it is tilted in a particular angle. Is that okay? Maybe you can look into that one too.
Okay.
So if there's no question, let's try and do this for me. Is that okay? We are using only 10 minutes for this. So let's hold on to the question 2, but let's do the question 1 right now. Please, how is it going? Are we seeing top?
We are on it.
Okay. Okay. Should I guide you how to go through, or yeah, say Yakubu. Hello, sir. Yeah, sir, Samuel.
Hello, sir.
Uh-huh. Okay, uh-huh.
Uh-huh. So please, this is how I went about it.
Okay.
So please, I multiply. I first multiply
Mm-hmm.
the N1, that's the N1 by
Mm-hmm.
HV1. And I had 1 by 10 exponent 13.
You said 8v1.
Yes, please. HV1.
Okay.
Yes, please. HV1.
Mm-hmm.
And I had 1 by 10 exponent 13.
Okay.
And the N2, I multiplied the 20 by 5 by 10 exponent 11. And also I had 1 by 10 exponent 13. And the N3 too, I multiplied the 30 by 2 by 10 exponent 11. And I had 6 times 10 exponent 12. So
Okay,
by
hold on.
adding all, yes, sir, by
Say
adding
Yakubu,
all
hold on.
okay, sir.
So what say Yakubu is doing here is we are interested in only this part. And it's when you look at the formula, the number of photons is always multiplying the energy. And the energy is this. Is that okay? That is our Planck's constant multiplying the what? The frequency. Lucky for us, we are giving the energy of each photon. Is that okay? The first one that we were given is this. The second one that we are given H2 is this. The third one we are given is this H3. And you know, for each of them too, they have a particular number of photons that passes per second. So it means the first energy corresponds to the first number of photons. The second energy corresponds to the second number of photons. The third energy corresponds to the third number of photons. So your work here is to just come and take the N1, the value for the N1, come and multiply it by the first energy. Take the value of the N2, come and multiply by the second energy. Take the value of the N3, come and multiply by the third energy. Please, are we okay?
Yes, sir.
Yes, sir.
Perfect. So, sir, please, can you continue?
Okay, sir.
So
So, by summing them up, I had 2.6 by 10 exponent 13, that KeV.
Okay.
Yes, please.
So that is all.
Yes,
At the
sir.
arithmetic, I don't know the answer, but from the procedure, that is all.
Okay, thank you, sir.
not
Hello, sir.
hello.
Yes, please, I'm listening.
Please, I can see down there you were given a converter. That is
Yeah, one
every electron volt is 1.6 exponent negative 19 joules.
multiply.
Hello?
That is, yes, I'm listening.
From the answers given, it's like the converters were not used.
Yes, so energy can be in electron volts and it can be in joules. Is that okay? So depending on if this one comes as an objective and the options given is in joules, you have to know that you have to do your conversion. Is that okay? If it's not, you can still work in electron volts and that is very fine. So I just added it up here. So we can also go about it by finding the answer in joules instead of electron volts. Is that okay? Because here the question wasn't very explicit whether to leave the answer in joules or electron volts. Are you okay? Are you okay?
Please, hello.
Yes.
Hello.
Yeah, I'm here.
Yeah,
Yeah.
please. Yeah, please. If the question says we should find it in the joules, that means that you are going to multiply the final answer by the 1.6 times 10 raised to the power 1 negative 19.
That is all.
Okay.
So if
So
you
I
are
don't know.
if you are to find it in joules, the best way to go about this one is either you convert the final answer, or if you want to stay safe with this, each energy that we are given here, convert each energy in joules. When you finish, you multiply by the N1. So you convert this one to joules, you convert this one to joules, you convert this one to joules. Then when you finish, you multiply by the N1, 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 N2, N3. Then you find the summation to get your intensity. Is that okay? Either ways that you do it is still. Is that okay?
So, sir,
Yes, sir.
please, sir, what was his final answer?
Okay. Was it say Yakubu?
Probably we might have
Yes,
another.
yes, please.
This what was the final answer?
The final answer was 2.6 by 10 exponent 13.
So this one is in joules, right?
No.
This one is in
Electron volt.
Yes, it was in electron volts.
Quick question. The K doesn't have any effect then.
They are all in K, so it's fine. The K is
Sir.
Okay, sir.
a kilo. Is that okay?
Okay, sir. Okay, sir.
So, sir,
Mhm.
when somebody also chooses to,
chooses to,
add all the HVs multiplied by electron volts, then come to the N1, N2, N3, add all of them. Then multiply both, would that method be also correct? Or
I'm not understanding your method.
first add all the N1, N2, N3.
Mm.
Yes. Then
No,
you come and
you
add
get a different answer. When you do that, we may get a different answer.
okay, HV1, V2.
You have to find the individual
Okay.
intensity before you sum all of them up. Is that okay?
All right.
Hello, sir.
But anyways, right now we have an answer, so you can try the different ways and see if you're still going to get the same or
Hello,
one.
sir.
Yes, sir, Hassan, I'm listening.
Sir, with the question that my colleague just asked, no, it will only be workable
Your network.
if the HV1 equals HV2 equals HV3. That's it. That one.
Great. The mathematicians are talking. Are you okay? Sir Hassan, thank you for the feedback. Okay. So
I didn't hear what he said.
So he's saying that you have the same energies for all of them running through. And since they are different, if you use this method, your answer is going to be different. Are you okay?
So does it mean when we are calculating, we should convert them into joules, or since their energies are different?
Okay. So no, he was answering the question in terms of someone asks whether you can add all the energies together and add all the numbers together, like the number of photons together. When you finish, you multiply. And he was answering that if you do that, it may be wrong unless you have the same energies for all of them. Exactly. Yeah, we are giving 3 different forms of energies, and they are all different for each photon emitted. Is that okay? So he was just buttressing on the fact that you may get a different answer if you use a die approach, unless for the 3 energies given, they are all the same. Are you okay?
Okay, I'm okay.
So with the conversion to electron volts and joules, as I said earlier, it depends on what the question is asking. If the question is very specific, convert it, then you do it. If the question is not specific, just leave it like that and do it. Is that okay? Unless the question is very specific, leave it in joules, leave it in electron volts. Apart from that, I think it's fine. Is that okay?
Please, when you do the thing, you get 1.6 times. I don't know why my friend had the 2.6. Because mine to give you 1.6 times 10 raised to the power negative, sorry, 13.
I also had 2.6. So
Then check your
check your answer.
Okay.
So please, what is the final answer so that we'll be able to identify which one is correct?
I've not done the arithmetic. So you have to multiply this 10 kilo electron volts by 10 raised to the power 12. Multiply 20 kilo electron volts by 5 times raised to the power 11. Multiply 30 kilo electron volts by 2 times raised to the power 11. When you finish, you get 3 different answers. Then you add all of them together. And the answer here is supposed to be in electron volts. So this one, you can choose to even just use calculator without actually writing or something. Someone should confirm the answer for us. Any different answer? Any different answer?
So it's the same thing.
It's supposed to get, okay.
2.6 times 10 to the power 13.
Is it 12 or 13?
It's 13.
13. Yeah. So then someone has written at the comment section, check your answer for me here. You have to use the power 12. Okay. So there's another thing to, so it means we are okay, right? Can we move on?
Yes.
Perfect. There's another thing that I want to show the class before I move on to the optics part. I have to show you this one briefly.
Hello.
Yes.
Yes. Sir, please, I wanted our colleagues, at least we can share our idea on the second question before we move to that. You are searching for one or two things.
Okay. I'm almost done. So I'll leave that one for you. When I'm done, I'll finish just sharing the slide here. Is that okay? Okay. This is not my slide, but I have something inside here that I want to show you. Are we familiar with this formula? Have you seen this one before? Can you see my screen?
Yes, sir.
Have you seen this formula before?
Yes.
Perfect. Paul is saying no, Erademaboka. We did this last week and even this week too. This morning I spoke about it. And
Unfortunately, I couldn't join the class. That is
okay.
why.
Okay, fine. So we started talking about the energy levels that we can calculate. And under the energy level, I told you we can find for the wave number. And wave number is just the inverse of the wavelength. Is that okay? So this thing that you see here is called the wave number. And if we derive the wave number, we're supposed to get this formula. There's something that we can also bring on point here that we call the series. Is that okay? So we have the Lehman series, we have the Balmer series, we have the Paschen series and other things. And it depends on the energy level that will give us that series we want to elaborate here. Is that okay? I don't have this in my slide. That is why I'm just adding up. And if we are considering this, it means that anytime we have a Lehman series like this, we expect that the final energy level is supposed to be a stationary state of 1 or a quantum number of 1. Is that okay? If we are talking about the Balmer series, we're expecting that where the energy is, the very final one is supposed to be 2. The Paschen one, we are expecting that the last energy level is supposed to be 3. So when you look at something like this, the chart I have here, look here on the right here. If we have an electron, this is the very first one, N1. That's the principal quantum number 1, principal quantum number 2, principal quantum number 3, up to infinity. Anytime energy is from anywhere here, and it ends up here at the first principal quantum number, we call this one the Lehman series. But it doesn't end at 1. Maybe it ends as 2. We call this one the Balmer series. It ends as 3. We call this one the Paschen series. So each energy level has a series name that we can target to. Is that okay? Which is very important. Are we understanding a little?
It's a go.
Please, are we understanding a little?
Please go.
Yes, sir. Yes.
The series.
Okay, as we go over. Okay. So now I'm going back again. My slide that I showed you, we were able to derive the formula for a wave number. And we even did it and related Planck's constants, and we related the energy, we related the frequency. Now I'm telling you that if an electron is at a high energy state and the final energy state that it results in, into first energy state, second energy state, third energy state, sure. If it's as the top one, and at the end of the day, the final or the level that it gets to is the last energy state of 1, and we are doing the calculation, we are using this because at the end of the day, this one's supposed to be NF, because the formula I showed you, we're having NF and we're having N1. Is that okay? Can someone read the formula I showed you to me for the wave number formula? Do we have it? Do we have it? Okay, maybe let me go back to the slide. I want you to understand this one before I can go on. Say be a muhuni baby, it will not be a problem.
So I have it here.
Okay, I'm even sharing something here. Okay. So please, let's look at this one. Do you remember this?
Yes.
Or we don't? Do you remember this? Very good. So this thing that we have here is a wave number. And after deriving all this, we ended up with what we have here. Is that okay? And I am telling you that anytime we are at, hold on. I want to write something. If we have an atom, this is the nucleus. This is the first principal quantum number. This is the second principal quantum number. This is the third principal quantum number. This is the fourth principal quantum number. Now, if an electron is sitting here, right, at the end of the day, we expect the electron to come down here. Is that okay? So it's going to transit from the fourth one to the very last one, the first one. Is that okay? And I'm telling you that at the end of the day, the initial and the final is different. So we are interested in finding the wave number. If we are talking about any time an electron either starts from the 4, the 3, or the 2, but it results or end up at the first quantum number, we are calling it the Lyman series. But if the electron starts from, let's say, 4, 3, and the very, very last principal quantum number it ends up is principal quantum number 2, we are calling it the Balmer series. Anytime it ends up at, let's say, 3-2, we are calling that the Paschen series. That is what we are interested in now here. So here, if you are giving, I'm sharing something again. If we are giving this, a situation like this, and found only be free by, say, free the 20th principal quantum number, but it ended up at the first one, at the very first principal quantum number, whatever being the situation, we are calling that the Lyman series. Is that okay? And that is what I'm elaborating on here. So when we talk about anytime we talk about Lehman series, know that at the end of the day, when the electron was moving, it ended up at the first principal quantum number. If you're talking about the Paschen or the Balmer, you know that, oh, the Balmer is the second principal quantum number. That is where the electron ended up. Is that okay? So that is what I'm just telling you. Please, are we okay now?
Yes, please.
Okay.
Yeah.
So now that is for Balmer, that is for the Paschen, and that is for the Lehman series. And apart from that, there's another one that we call the bracket and the PHY series. Is that okay? So if it ends up at the fourth one, if it ends up at the fifth one, they all have a name that we call it. And we can actually relate this one with the wavelength, but we will not go there. Is that okay? Now, there's something that I want to also tell you. Now, let's look at something here. Anytime we are interested in finding the energy of of a particular principal quantum number, I've explained to you how we do that. But we can also relate something like the kinetic energy and the potential energy in this sense, where what we have to do is quite simple. What we have to do is introduce the kinetic energy and introduce the potential energy. And in fact, with time too, we can also introduce the centripetal force. I will explain that. Now, in terms of kinetic energy, in terms of potential energy, remember I stated that Ernest Rutherford was even considering electrostatic force of attraction in terms of this energy, keeping the electron move at the atom. Is that okay? So it makes sense if we want to relate it in this way. Let's look at something here. Let me use a pen. If we are relating kinetic energy and potential energy in this situation, we all know that if kinetic energy, we are talking about 1/2 mv squared, right? Now, if we are relating the potential energy, we can relate it in terms of electrostatic force of attraction. And if you remember Coulomb's law, can you tell me the Coulomb's law? We did this in general physics.
Coulomb's law.
Come again.
F, the force.
Yes.
Is equal to K
KQ1 Q2 over D squared.
Very good. Now, under the Coulomb's force, we introduce something we call the potential energy. And I don't know if you remember where we related it in terms of dividing it by R, so that at the end of the day, we will get something like the Q1, Q2, but this time around divided by R. Is that okay? And that is what is introduced here in terms of the potential energy. And that is what we have here. Is that okay? But if, let's hold on to this energy. If we are also considering the centripetal force that is keeping the electron moving around the nucleus too, we may also consider a formula like this. Is that okay? Where we know that our centripetal force is mv squared over r. And we can relate the force of attraction here. That is our Q1, Q2 divided by r squared. That is what we have here. Is that okay? But in general here, we know we have mv squared here. We have another mv squared here. So we can ignore this mv squared and come and substitute this whole thing in there. This whole equation. So we can make mv squared the subject here. Then we substitute this whole equation in here. And at the end of the day, if we make mv squared the subject, we should be getting the next formula here. Is that okay? Because r here is going to cancel this r. Because we have 1r squared here. So this r here, when it goes here, it will cancel 1 here. And we get this formula. So if we do that and substitute it in place of where the mv squared here is, it means at the end of the day, we should be getting something like an equal to sign, this whole formula. That is the k z e squared on r minus this whole thing that we have here. Is that okay? Now let me show you something. So after substituting, this is what we are getting. Is that okay? And if we do a subtraction of, it's the same term that we have here. This term here is the same term that we have here. Is that okay? Now, when we do a subtraction of what we have here, in the end of the day, we expect to get KZE squared on what? R2. Is that okay? Sorry, 2R. And this is very important in terms of finding the energy and relating it to the radius of that principal quantum number and relating it to the electron that is moving. Is that okay? I didn't bring this one in my slides, but I'm just highlighting it for you to know. Now, if we consider everything that Bohr did, we can also, I think this time we've done it, electromagnetic radiation, but we can also look at the something called the photoelectric effect. Have we heard of photoelectric effect before? Okay, Frank has heard of it before. Apart from Frank, Samuel. Apart from Samuel.
I've heard it before.
Okay. So now let me show you something again. Please be keeping in mind the things I am showing you. I will update the slide and give it to you, but just be keeping in mind. Okay, so let me show you something. Can you see my slide? Perfect. Apart from Frank, can someone confirm that they are seeing it?
Yes.
Yes, sir.
Good.
I can see it.
So now let me briefly introduce you to photoelectric effect. Now you see, let me show you something before maybe I come. Anytime we incident, light is also a form of energy. We incident light on a material. Some of them is able to eject some electrons from the surface of the material. But that is not of interest to me right now. Right now, the one that is of interest to me is the kind of light that we can use to eject these electrons that we are talking about. Now, observe this and give me a feedback. There's a material here, and there's a blue light. Now, the blue light hits the surface, and it ejects something. Are you seeing that effect? Is the video showing?
Yes, sir.
Yes, sir.
Now, this is for the blue light. Now, let's look at the red one. Is it ejecting something?
No.
Perfect. So the question to the class is why?
Hello, sir. Hello, sir. Hello.
Yes, Al Hassan, I'm listening. Or no, it's not Al Hassan. Francis, Francis, I'm listening.
Hello,
That's
sir.
a speak.
Okay, sir. I think the blue light was able to eject because the frequency is enough in order to cause the ejection. But the red light is of inadequate frequency. That is why it was not able to eject.
Perfect. Is that okay? So now let's look at the magnetic spectrum. In terms of energy
Sir,
levels.
please, sir.
Yes, please. Yeah, I'm
I
here.
wanted Alasan to come again with the answer that he just provided.
Al Hassan, please help me again.
Okay. Please, I said the blue light was the adequate frequency. That the frequency is enough to cause that ejection. But the red light, the frequency is not enough to cause that eject. That is why it did not eject.
Lucky.
Yeah, yes, sir. Can you also say that because the blue one, the wavelength fall on the surface of the metal, that's why it was able to eject it. But the red one, like the wavelength could not fall on the metal. That's why it could not eject it.
Oh, okay. I don't know for this particular answer though, but we are still discussing. So let's still continue. Any defense submission?
Okay, sir. Can you also say that the blue one has higher energy and then the red one, the energy is lower?
Okay. So in terms of energy and frequency, they are all the same. So high energy, high frequency. So yes, I'll go with this one too. Okay. So now let's go through the answer. So ideally, when the red light hits the surface of this metaphor, there is no energy that is given off, like any emitted electron. But in the situation, the blue light does, because blue has more energy than the what? Than the red. And it is very important. So in terms of energy, that is fine. In terms of wavelength, frequency too, that is fine. Is that okay? So can use these two things to explain. But the thing is, this is a question. Can we get more energy from a red light? The question it's not framed well. If, let's say, I increase the number of red light that is hitting the surface, do you think I can still get some energy emitted from the surface of the metaphor?
Yes.
Okay, can you help me explain why?
I can remember last week you said something like we can have a visible light. Or let me say, yeah, you can have a visible light, but if and the intensity of the light can be adjusted and can be made harmful, more harmful. So
Okay.
I think, yeah,
Okay.
yeah, within the same range, it can be there can be some adjustments.
Okay.
Yeah.
Yeah. Say Lucky, your house. What's up?
Yeah, so if you increase the more red light, for me, it will not see any injection. You only see the injection when you increase the frequency or the energy.
Okay.
So maybe increasing it will not. By
Mm.
increasing the energy or the frequency of it will rather causes ejection.
Okay. Say Christopher, your house. What's up?
I think increasing the number of red light will not have any impact, but rather when we increase the frequency or the energy, that one will rather make it emit electron.
Okay, that's perfect. So now let's look at something. What we are saying outside with you. Now let's look at what we are doing here. We've increased the number of red lights to hit the surface. But at the end of the day, you're still not getting anything injected. There's something moving on the screen. I hope you can see it from your end.
Yes, sir.
Can we see?
Yeah, you can see.
Perfect. Is that okay? And
Yes,
the
sir.
reason is when even this one too, you will still not get anything. Now let's look for the blue light. We are going to increase the intensity of the blue light. Now, when you increase the intensity of the blue light, what are we observing?
It is emitting electrons.
Electrons. But this time around, even the electrons that is emitting is a lot. Look at this one.
Yes.
A lot of electrons being emitted. And it's still the same as how you explained because of the high frequency. Is that okay? And you see,
Yes,
when I
sir.
was at the X-rays, I told you that the intensity is different from the hardness of the ray. The hardness of the rays deals with the wavelength, the energy, and the frequency. Is that okay? We can bring a lot of soft X-rays, and it may not do nothing to you. But we can bring a small hard ray, and it may harm you. Is that okay? So the most important thing that we have to keep in mind here is the wavelength, the frequency, and the energy we are bombarding with that material to eject the electrons. So that is one thing that I want you to know. So that is all about this. And there's one thing that too I'll elaborate on. I want to show you something. Okay, very good. There's this formula too that we have to talk about. Have we seen this formula before somewhere? Anyone?
No, please.
No, please.
Okay. So, okay. Say like I've seen it before. Help me.
Okay, so that is what do you call it? The W, that's the work function.
Mm-hmm.
So we have the HF, which give us the photon energy equal to the maximum energy plus the work function. The W stands for the work function. That's what I know of it.
Okay, perfect. Now this one
So you can
is
also make you can also make that one the subject, the work function the subject by subtracting the kinetic energy, that's the maximum energy from the out of the HF, make this the work function also the subject.
okay. That is very perfect. Now this is just a small changes that we've done here. So we have the energy to be equal to the kinetic energy plus how, say, like you said, the work function exactly. Now we've just brought the kinetic energy first, and we've related to this whole thing. I just want to explain these things to you. Then maybe that would be all. Then we find the cutoff wavelength. You know, if we have a material like this here, and we have some electrons that we are going to bombard on the material, we need a particular form of energy here before this one can be ejected. The electron here can be ejected. And in fact, we need some particular form of energy so that, because after ejecting, the ideally is supposed to stay around like this. But you see, we still need some particular form of energy so that after ejection, it can actually move out. Is that okay? And that is what is interested here. The work done that is going on here. In fact, the energy here is the energy that this, let's say, blue light is coming with. The work done here is the energy or the work done that is needed to remove the electron from the surface. The kinetic energy is the energy that the electron has gained after being ejected to move out. Are we okay? Or we are confused?
Yes, sir, I understand.
Okay, so I'm coming again with this 3 terms here. The first term here, maybe let me go back. This energy, this particular energy, if we have a material like this here, our metaphor, and we bring a blue light, to hit the surface. Now we know that we need, comparing a blue light and a red light, we need a blue light to hit the surface so that we can remove an electron from the surface. This is the energy that the blue light is coming with, the HF. Is that okay? And we know this formula already. Now, it needs a form of energy that it can remove this electron from the surface. And even after removing the electron from the surface, the electron too need another energy that it can use to move out of the surface and go anywhere that it wants to go. Is that okay? And that is the most important thing. The energy needed to move that electron from the surface is our vector. Is that okay? So the minimum work needed to eject the electron, only the electron, that is all. Now, the kinetic energy is the maximum kinetic energy of the ejected electron. So after it has been ejected, it still needs some form of energy that it can use to move outside. And this energy that it's used to move, this energy that it is used to eject, they should all end up to the energy that we need from the incoming photon, the blue light. So it means if the blue light energy is not strong enough for these two things, you will not get the phenomena of photoelectric effect that we are expecting. Please, are we okay a little? Oh, we are.
Yes, sir.
Okay. Apart from say Paddy, Frank Paddy, are we okay? Perfect. So this is very important. Now, in terms of the kinetic energy, if we want to find the kinetic energy, it means that we should find the energy of this blue light and subtract it from the ejected one. That is the breakdown before we can find the what kinetic energy. Just change your subject. Now, you know, if we also bring the conversation in here that we are only interested in the energy that it needs to be ejected. What is going to be the formula? Now, this is the formula. If I ask the class, I am only interested in the energy that I need to eject the electron, what will be the formula? I am interested in only the energy. What energy do I need to eject only the electron? How is the formula going to be represented?
Then, sir, then it means the energy of the electrons after being ejected is going to be 0, like I'm seeing on the screen. So the energy of the photon will be equal to the work done in causing the ejection.
So it means the kinetic energy is going to go off at 0, because now I'm not interested in the energy that after ejecting it moves with. I'm only interested in the energy that I need to eject the electron from the surface. So it means I can strike the kinetic energy to be 0. Then I can just bring the work done to the other side so that I get a formula like this. Exactly. So this one represents the energy needed to remove the electron from the surface. Only the energy needed to remove the electron from the surface. Are we confused or we are following? Okay. Now, if that is the case, we can just do a change of subject and other things to find something we call the cutoff wavelength. Is that okay? Now, let me go back a little. If we have something like this, can I bring in wavelength here? Is it possible? Can I bring in wavelength?
Yes.
Okay. So give me a formula that relates frequency and wavelength.
Frequency equals speed of light in air over wavelength.
So it means my H is going to be speed of light on what? On wavelength.
Yes.
Equals my work done. Now let's look at something here. This is very simple. Now, if I have a situation like this, I can make the wavelength the subject, right? Then at the end of the day, I should be getting something like the Planck's constant, speed of light, divided by my work done. Do you agree to this? So I've just brought this one down here and I've sent this one up here.
Yes, sir.
Perfect. Now, this formula, we call this formula the cutoff wavelength. Is that okay? And the cutoff wavelength is a wavelength that we need to eject an electron from the surface of a material or a metal. Is that okay? So if I know the work done or my work function, and I know the speed of light as a constant, I know my Planck's constant, I should be able to know that which of the wavelengths should I use so that I can eject an electron from the surface of a metal. And that is what our cutoff wavelength is. Is that okay? Here is the same thing. This is work function. It's the same work done that we are using. Okay. Please, are we okay? Should I go on? Are we okay?
Yes, sir.
I don't understand the C. The symbol C.
The C is speed of light. It's a constant.
Okay. Thank you.
Okay. So this is just elaborating the fact that how we can compare or correlate the kinetic energy and the frequency and other things. But we don't need this thing for now, so we'll talk about it later. And in fact, photoelectric has a lot of applications. You are even able to use your calculator because of photoelectric effect. At the end of the day, we have the sun hitting the panels that we have here. It ejects some electrons, and that is used to form a form of energy to the battery, and you use it. Is that okay? We are able to use flashlight because of all these things. We're able to use some cameras because of all these things. In fact, some right now when you are entering a mall, you don't need okay, I don't know for Cape Coast here, but in Accra, most of their malls, you don't have to open. You approach, then it opens. You park, then it closes automatically. And they are all because of this radiation emission. Because when you look at the picture that I have at the top here, there's one device that is sitting here, and there's another device that is sitting here. And one is the emitter, one is the receiver. Always, it is programmed that it should be receiving a photon. But anytime someone comes and passes, it breaks the photon transmission, and it signifies or tells the gate to open because something has been blocked. Is that okay? And that is an automatic way of also creating a doorknob. And even in security systems, they mostly use these things a lot. You don't have to trespass a particular place, and they use the receiver and the emitter there so that anytime someone passes that place, it blows an alarm. So it has a lot of application. Is that okay? So that is what I want to show you with the photoelectric effect. Any questions so far?
So we should go and look for we should read under those by photoelectrics or
I will actually update the slides and send it to you. Is that okay? All the things that I've just added, by the end of next week, I will hopefully add it up. Is that okay? So don't worry.
Okay. And some questions that we can get the proper use of the formula.
Okay. Oh no, come again with what you just said.
I say a question under that particular calculation. So there are any two questions we can, so that we know how to apply them when it. And that I'm talking about what we just did.
Okay, that's fine.
Thank you.
Now, I think for now we are done with the atomic physics part. The next thing we have to jump on is the optics. There are a lot of things that you've done here, as I said earlier. So we are literally going to skip almost half of optics part. Then we will do the very latter part that we are not familiar with. Is that okay? Or you want us to still go through together? Or class,
No,
what do you
sir.
want? Very good. So we can just skip a lot of things. So now we know a wave. Is that okay? I explained this thing to you in general physics. And when we are talking about wave, we are just talking about the disturbance of a medium. And you know, in relating waves, we can talk about all these kinds of waves, sound waves, the seismic, the pressure, the ultrasound, and everything. And in fact, depending on the medium of transmission, that is why we can get wave. And right now that we are talking, if I ask the class that is a visible light a wave, will you see a yes or a no?
Yes.
Okay. Why is it a wave?
Because light is an electromagnetic wave.
Perfect. And electromagnetic waves also falls under waves. Very good.
Yeah.
So light is a wave. So it means all the radiation that we've been discussing, they are all waves. Is that okay? So that is why we have this example as a radio station in all the wave application. Now, I don't know, we've done this all. General physics, did we do this?
Yes.
The way I'm going fast. Okay, we did this. So we can also characterize wave in so many ways, like the medium, the energy transfer, the particle motion, or the periodicity. Is that okay? And we can also take some characteristics like the wavelength, the frequency, the amplitude, and the speed. And I told you that in terms of propagation, we can have a transverse wave and a longitudinal waves. In terms of medium of travel, we can have mechanical waves and electromagnetic waves. And this is very important because a longitudinal wave shouldn't behave like a transverse wave because of their waves of propagation. And when you're talking about longitude now, we are talking about if the particle moves parallel to the energy. And if you are talking about transverse wave, if they move perpendicular-wise. Is that okay? So we spoke about all these things and a lot of applications under them. And we spoke about the electromagnetic radiation. Did we do this?
No.
We didn't do this. Okay. So I think you can do it. So far, I have explained electromagnetic spectrum to you. So what are the subcategories of the electromagnetic spectrum? Name each subcategory and provide one real life application for each. That's how I do a say about my exam. So
No.
did you not?
No.
It didn't come.
Yes,
It didn't
please.
come.
Oh, okay.
What do you buy? I can't be training now.
Oh, the exams was very cheap. Sir Christopher. Very, very cheap.
It was not easy for me at all.
The exams wasn't easy for you. Hey, Mr. Arthur. The exams you wrote is everything that was in the slides. In fact, it was everything I have solved with you in the slides. And maybe you can prove me wrong if I'm lying.
It's true.
Every single thing.
We even said it.
So
we even said that what Rabbi told us came to us, but in fact, you would have highlighted well to us that this thing may come to the exam.
I can't highlight you.
So my problem was about the optics. That time we were doing the lectures on optics. In fact, I was not available. So it was a problem for me. Apart from that, all that we have discussed, that I was able to tackle it.
Wow.
We didn't cover a lot on optics at that time.
Hey, Regina Boka. Anyways. So yeah, that is for the electromagnetic spectrum. So we've done all these things, which I will not go through again. And I think the most important thing that I have to highlight on is light-matter interaction. Is that okay? But when light hits on matter, you know matter, right?
Yes,
matter is the solid, liquid, the gas, everything. When light hits on matter, a lot of things happen. And now when you're talking about light, we are talking about the visible light in the radiation. Is that okay? A lot of things happen. One thing that happens is reflection, refraction, interference, diffraction, absorption, and scattering. Is that okay? So when light hits, we can see some of the light reflected, some of the light refracted, some of the light interfered, and all the other. Now, with all these phenomena, which of them are we familiar with? Are we familiar with the reflection part?
Yes.
Okay, so the class is very familiar with the reflection part. What about the refraction too?
Yeah.
What about the interference?
No, sir.
So the interference is cancelled. What about the diffraction part?
No, sir.
So that one too is cancelled. What about the absorption and the scattering?
The rest of them.
The rest of them, great. So from this end to this end, that is what I will be talking about more. The reflection and the refraction, I think we've done a lot of conversation in it in general physics. So now let's go to the interference straight away. I'm coming. So when the class is supposed to end at what time?
11.
11:50 or 11?
Supposed to start from
11.
7.
Ah, 11. 7 to 11.
Yes,
All
please.
this while I was thinking I'm ending at 11. Oh, okay. So let me finish with the interference, then we will end them. So
I'll finish eating.
if not eating, I'll finish very soon. Then go and eat there.
So somebody's background is disturbing us. I don't know who is that.
Please, can you unmute yourself? I beg of you. I'll finish right now. So when it comes to light and matter interaction, one important thing that actually happens is interference. And there are some things that has to happen before interference. You will see interference. And maybe let me tell you one application that will let you get interested in interference. You see, sometimes when it rains, then you are passing through a tight road.
Hello,
You see
sir.
some nice colors on the. Yes, sir. You see some nice colors on the road. And sometimes too, if children are playing with bubbles, you see sometimes the bubbles gives us a very nice pattern of colors, like a rainbow thing on it. Another one too is, I don't know if you've seen, is it peacock? They have some nice feathers. When they raise it, that one to give some nice pattern of colors. So these are all from something we call the interference. Is that okay? So under interference, we have something we call constructive and destructive interference, which I'll talk to you about it. But we need two important conditions before this interference occurs. One, the most important thing that has to happen is that the light source is supposed to be coherent. And the second thing that's supposed to happen is the light source is supposed to be monochromatic. And when we say monochromatic, it means we should have only one wavelength. Is that okay? Now, when we mention wavelength, you know what we are talking about. So if it's red, we need red with a particular wavelength. That is all. And when you say it's coherent, it means they are all supposed to be in a constant phase. You see, if we have a transverse wave, we have a transverse wave moving like this. This is A. If I have another one that is moving on the same path as this, it means they are coherent. If, let's say, it comes and starts here and moves like this, it is not coherent. It is in different phase. Is that okay? So they're all supposed to be in a constant phase. If this one is moving like this, another one is moving the same way, the same phase that we are expecting them to move. Oh, sorry, I've changed this one later. Is that okay? And we are saying it is in a constant phase. So there are two things that we need here. The light source that we are going to use, the light source is supposed to be what? To be coherent, and we expect the light source to be what? A monochromatic. Now, there was one important experiment that Thomas Young did in the 1800s. And it was a very interesting phenomenon or experiment. He was just using this experiment to explain to us the constructive interference and the destructive interference. Anyways, let me go back and show you something. Anytime we have a constructive interference, we expect that if we have a wave like this as wave 1, and we have another wave like this as wave 2, and we add these two waves together, what do we think is going to happen? We are adding these two together. Is it?
So they will meet at a point.
So yes, so they will meet, but what is going to happen to their when we have, hold on, let me ask this question before I continue. When we have a transverse wave like this, what is the name of this part?
Crest.
The crease.
Crest.
And this
The
part,
crease.
what?
Trough.
The trough.
The trough. Very good. Now I want to know, if I add these two waves, what happens to the crest and what happens to the trough?
I think it will be in the same position.
The amplitude will increase.
Perfect. Their amplitude will increase. Is that okay? So if we have something like this, and let's say the amplitude of this first one was 2, and the amplitude for this one was also 2. We add the two together, we're expecting the amplitude to be what?
4.
4. It will go very high. Is that okay? If a situation like this happens, we call it a constructive interference. But in a situation where we have a wave that has a different phase, like this. Now you see where the crest is, it is the trough here. Where the trough is, it is the crest here. Now when we add these two waves together, now this is my wave 1, my wave 2, and my wave 3. I'm adding wave 3 and wave 2 together. What do you think will happen?
Zero. Or
It's going to be 0. Yes, they will cancel out. So at the end of the day, the kind of wave that I'm going to get is going to be just a straight line like this. Is that okay? So this is a constructive interference. This is a destructive interference. I have it somewhere, but I'll show it to you, but I'm just elaborating on it before I continue. Please, are we okay? So this is a constructive interference and a destructive interference. Now, Thomas Young did an experiment to prove for this constructive interference and destructive interference. And that is what we are going to go through it. So this is what he did. He has a slit here, or let's say a barrier, and we have a light source that is going to go through in. And it's the same light source. So if this is my light source, it's the same light source. And I've given two conditions that the light source is supposed to be in before this thing can happen. I said the light source is supposed to be what? Coherent and what?
Monochromatic.
Monochromatic.
Perfect. So now if we have this, anytime the light source exits from one end of the slit, the wave is traveling. I have my crest, I have my trough, I have my crest, I have my trough, I have my crest, and it's going. Now let's look at this. I want to compare the first wave and the second wave. Where the crest is here is the same as where this crest is. Where the trough is, in terms we are rolling a straight line through, is the same. So when we even reach here, where I have my trough, I have my trough, I have my crest, I have my crest, I have my crest, I have my crest. What type of interference do you think will happen here?
Constructive.
Constructive interference.
Constructive.
Is that okay? And anytime we see a constructive interference, we're expecting a bright fringes. Is that okay? When I see a bright fringes, you see a light. When you come in for particles, I will show you this. But for the constructive, you see a light, and you call it you see the light that you place it here. So if it was a red light, you see that red light here, and that is the bright fringes. Let's look at a different angle, because the light is coming and the wave is traveling through so many angles. Now I have a different angle here. Now let's trace their peaks. I have another crest. I have another crest. I have another trough. I have another trough. What type of wave interference do we think will happen here?
Same constructive.
Same constructive. Thank you.
Constructive.
Is that okay? But let's look at the last one here. The place that I have a crest, there's a trough. The place where I have a trough, I have a crest. The place I have a crest, I have a trough. So this time around, what type of interference am I expecting?
Destructive.
Destructive.
Is that okay? I'm expecting a destructive interference. And the destructive interference, you don't see any light. It will be a dark fringes there. Is that okay? It is very important we know this. In fact, when it comes to interference, I told you that it has a lot of applications. Is that okay? Like the bubbles we see that have a nice like colors like this, like the on the road when it rains a little, the nice patterns that you see. This we may not elaborate more on it, but those who do physical science, I will teach you something like thin film interferometer, and that is where you get to know the formulas and other things that brings around about this. Is that okay? But the introductory part that we are doing, we are just going to move at the surface of this. Now, I have explained the constructive for you, and this is the constructive. I'm expecting a big wave. This is the destructive because a crest is meeting a trough. At the end of the day, they all cancel out and I get a straight line. Is that okay? I'll end here, but the next time we meet, I'll show you a diffraction, I'll show you absorption, I'll show you the reflection and other things. Then when I finish, I'll go back to interference again, and we'll go through some formulas under interference. And I'll take my time, then we'll go through the diffraction. Then I'll go through some formulas under the diffraction. But I think the reflection, I will not do it. Everything here, we've done it. Is that okay? Everything here, we've done it. So please, it doesn't mean you shouldn't go and read the reflection on. It's for you to just go and do a recap. Is that okay? If there are certain questions, those system set questions around it. So you remember the Fermat principle, your favorite. I remember you enjoyed it when we were doing it. So we've met it here again. You have to go through Fermat again.
So you have to, when you get there, you have to take us through because some of us were not, especially the ferment.
Okay. Then dispersion to we've gone through, dispersive power we've gone through, and I think you had a question under dispersive power in your exams, I think, right?
Yes, please.
Then we'll rainbow to is here. So all these things, I'll leave it for you to read everything here. I'll leave this thing for you.
Those things we didn't go through them all.
Which one?
So all what you are showing.
This one. We didn't go through this.
Not
The
at
lens
all.
Okay. Then maybe let's do it this way. Read everything up to my magnification. Is that okay? The next time you meet, I'll take you through the lens maker formula very well. Then I will do combination of lenses. Then I'll go back to interference. Agreed? Yes, sir.
It doesn't mean they'll be coming in exams again.
Yes, it's in this. It may, yeah. But it's a good thing for you because at the end of the day, you've done it before, so the understanding will be clear enough.
Okay.
Yes,
Sir,
like
any tutorial questions?
hey, this thing there, I always say it too. The tutorials is the question that I have in the slides.
Okay.
I feel I'm not like to, if I add more, it will be a burden for you.
So we need the tutorial.
So I should copy this one and put it on a different document and send it to you.
Yes, we.
Oh, it's okay. It's okay. This way.
Because I can't set another question. If I set another question, it will be a stress for you.
Yes,
Okay.
I think
this one is
because
okay. It's okay.
questions about doors will be very confused, baby. So if you are reading other books, it's fine. Just read through the slides. Get back questions to solve. Yes.
Hello, sir.
Yeah.
I don't know, but like you said, maybe if you can copy all the questions and put it on one lesson. The reason why I'm saying is that maybe, in instances like this, some of us may not be able to go through everything before the exam day. I think he's saying that it is our responsibility to go through everything before the exam. But what I'm saying is that maybe one or two reasons some may not be able to finish. But if we have the questions, we can tackle all the questions so that we can be familiar with it and know how to understand.
I can do that. It's not a problem.
Okay, sir.
But
Hello,
again,
sir.
don't the things we are teaching you. Read the slides. Just an advice: solve the questions in the slides. Get a past question. Solve the past question. You'll be fine in exams. The examiners are not like SS that WAEC is somewhere that is writing the questions to different schools. They all I don't know. They give us the outline, so they know what we are teaching. What I am using is the same as what RESCO is using. Is that okay? It's the same thing that they are also teaching. So it's just the slides and the past questions. That is all. You solve questions in the slides. You solve questions in the past questions. You shouldn't have a problem in exams, I think.
All right, sir. So,
colleagues that have past
my last
questions to please share.
Yes, please, my last question.
I'm listening.
The practical side, with those who are, I'm from family side. That's cool. But then when we get there, we some of the materials that they don't have, so we are disadvantaged of some things when it comes to the practical side.
Oh, okay. So don't worry. I'll talk to the coordinator. I think Dr. Peter is in charge here, so he's just here. We share almost the same offices at my top here, so I'll just talk to him at the right time.
Okay. All right. Thank you, sir. Thank you.
Don't worry about that.
Hello, sir.
Yes, sir. Please, I'm listening.
I'm waiting for the slide so I can go and print it. For me, if it is on the phone, I can't learn it.
You are waiting for the what?
The slide.
I've shared an initial slide. The update that I said.
Yes, sir.
Okay, so someone, do you know something? When you're printing, don't print all. Print the ones that I've taught you. Because you know,
okay,
so that I don't be confusing you with the things you are reading and the things I'm also sharing. So every year we are for a percent the chief students in maybe look at the things we've done. Okay, atomic physics maybe into on printing page 1 to say page 30 month for now. Now the hit we are not printing amount, that kind of a thing, you know.
Hello, sir.
Okay. Yes, sir. Please, I'm here.
Hello.
Yes, please, I'm here.
In fact, some of us we are not able to get the slide too.
Even really?
Block 1. Some of us we couldn't get the slide, so it affected us in the exams.
Oh, take his number. Where course rep? Who's our course rep? So you don't worry. Do you have my number, Sir Al Hassan?
No, sir.
So you can just text me. Okay, I'm coming.
Okay, sir.
Steven, is Steven here?
The reason why sometimes I don't want you to contact me straight is weekends when I finish teaching you. Maybe you message me like 100 times and I will not be able to respond ASAP, like as soon as possible, because when Monday comes, another burden and work also comes in mind, you know. So I'll be busier. Getting to Friday, then I'll think, hey, Charlie, I have switched students to take over. Then another, you know, that kind of a thing. So pardon me, but let me still write the number to you here. Then you can just say hello to me. Then I'll give you a contact of someone that can be sharing this thing to you. Is that okay?
Okay, sir.
055. So you can just say hello to me for now.
Okay, sir.
Okay.
Sir, so as we are that ICT, it has vanished.
It has vanished. So it's 0553 505207. Or what code even shared to you? My number is on it. code shared,
Okay.
interest and their numbers, PDF is my number is on it. You can just pick it from there.
Okay.
Or should
I think
I read it for you? 055
in there. Our
again.
colleagues, those they should do well to put it on the platform.
Okay, please.
Platform. Those who have it, you should put it on the platform for all of us to get it.
UCC Center, please be helping with this thing. I beg. I think the WhatsApp group I'm in is for only UCC Center. So please, when you
Center anyway. I'm in the Sunyani Center.
So don't worry. We say we reach out to you, then we solve this. Is that okay?
Thank you very much, sir.
You're very welcome. So maybe let's settle down and prepare for our next class so that I log off. So we'll continue next week governing.
All right, thank you.
Have a nice day. Merry Christmas.
Merry Christmas. Hey, I have to respond in many happy returns, right? Not many, sorry. Many happy returns, everyone.
Right, sir.